Welcome to the debate. The limits of electrification. You know, how fast an electric vehicle can go, how long its battery will last, and how densely we can pack power into its components. Well, it all really comes down to one fundamental challenge: managing heat. We're talking about the crucial thermal management required for the motors, the battery pack, and all those high-power electronics that make it all run.
Exactly. And this intense heat generation, it presents one of the greatest engineering hurdles today, especially as manufacturers push for higher power density and, of course, faster charging speeds.
Precisely. That necessity frames our essential question for today. Is the complex, multi-loop segregated liquid coolant architecture, the established approach we saw in early mass-market EVs like the Chevrolet Bolt, is that still the optimal strategy for ensuring long-term reliability? Or is the future inevitably moving toward the integration of all components under direct oil cooling to maximize thermal performance and power density?
I'll be arguing that integrated, direct oil cooling is, well, overwhelmingly superior. By putting the thermal focus directly on the motor, which is, let's face it, the main heat generator besides the battery, we really open the door to higher power density and ultimately simpler, more efficient electric drive units in the long run.
And I'll be defending the philosophy of segregation. My position is that having separate, specialized cooling systems is, frankly, essential for robust reliability and component-specific thermal optimization across the entire vehicle ecosystem, especially when dealing with the high demands of the battery and those sensitive power electronics.
Okay, I see why you think that, especially focusing on, let's say, historical reliability. But let me give you a different perspective, starting right at the heart of the problem, the motor itself. Advances in dielectric fluids and highly targeted cooling techniques have demonstrated that the traditional external liquid jacket where water or coolant flows around the outside of the motor casing is becoming, well, kind of obsolete for truly high-performance applications.
That's an interesting point. But we really must consider the vehicle as a complete system, not just the motor in isolation. When we look at designs like the Bolt EV, the engineering philosophy, it sort of demands separate cooling because the components have vastly different, sometimes even contradictory thermal needs. For instance, the electronics loop, it has to manage crucial sensitive power electronics like the main inverter, that's the SIPM or single power inverter module, the charging modules, and the drive unit. This loop is a relatively low-pressure system using a conventional radiator to reject heat into the air. It's designed specifically to keep those silicon-heavy components below their safe operating limit.
Right, but that sounds like a complex web of hoses and pumps, doesn't it? Just, increasing potential failure points.
It is complex, yes, I won't deny that, but that separation is a crucial safeguard. It prevents thermal cross-contamination. Now, consider the battery pack loop. It is entirely separate, and it's critical because the battery doesn't just need cooling, it often needs heating to reach its optimal operating temperature, particularly when fast charging or driving in cold weather.
Okay.
That loop utilizes the AC system, the compressor, the condenser, the R1234YF refrigerant, and special POE oil. The system is designed to handle massive thermal events. I mean, just for example, the battery coolant heater draws a full 2,000 watts just to warm the cells up until they hit about, 65 degrees Fahrenheit or 18.3 Celsius. You simply cannot allow the intense, rapidly fluctuating drive heat from the motor to immediately influence the battery's delicate optimal temperature range. The battery system requires phase change cooling using that refrigerant, which is a fundamentally different kind of problem entirely.
Okay, I respect the robustness of that segregated architecture for battery protection. I really do. But my core thesis centers on maximizing the motor's potential. If we focus the cooling precisely where the heat is generated, inside the windings in the rotor, we achieve efficiency and power density gains that the indirect external liquid jacket system simply cannot match. Numerical simulations like those conducted by TotalEnergies and EnginSoft have consistently demonstrated the superiority of direct oil cooling over traditional indirect water cooling.
Superiority is a strong claim. What are the concrete quantifiable gains you're seeing in that research that would justify abandoning segregation for the motor?
Well, the data is remarkably clear and honestly compelling. Using direct oil jets, which can spray dielectric fluid directly onto critical areas like the coils and magnets, achieved an average winding temperature that was at least 14 degrees Celsius lower than the external water jacket system. That is a significant reduction in thermal stress right there.
14 degrees, okay.
And when running the motor at very high speeds, say 10,000 revolutions per minute, that difference became staggering, up to 40 degrees Celsius lower. This superior thermal management, according to the research, directly opens the way to higher power densities for the future generations of e-motors. And furthermore, by using oil, we can combine motor cooling and transmission lubrication into a single fluid, simplifying the overall electric drive unit design quite dramatically.
Okay, I'll grant you the point on the motor. The data for direct cooling is compelling. But when we look at the whole picture, the real challenge isn't just the motor. It's managing the system's complete thermal footprint.
But hold on, you cited that incredible 40-degree delta at high speeds. How can a segregated indirect system, which relies on an external jacket, possibly justify accepting that level of thermal compromise on the single most critical heat generator? I mean, temperature control for components like permanent magnets is absolutely pivotal for maintaining peak performance and avoiding demagnetization over time. The simulation showed that by optimizing the oil's physical properties, they could achieve a 5.4 degrees Celsius reduction in the magnet temperature alone. That is precise component-level protection that indirect cooling simply cannot deliver.
That is true, and I concede that for highly localized heat extraction from the motor components, direct oil cooling is demonstrably superior. But the multi-loop system manages the entire vehicle's thermal environment, which involves complex, sometimes divergent needs. The Bolt's design ensures dedicated thermal control for the battery via that sophisticated AC chiller and refrigerant system, which handles functions specific to battery chemistry, like rapid heating and intensive phase change cooling during DC fast charging. That is a fundamentally different task than simply rejecting motor heat. Even with an oil-cooled motor, that hot oil must still be routed through a complex heat exchanger or radiator condenser system to reject that heat into the environment. So you reduce complexity in the motor casing, perhaps, but the complexity remains elsewhere in the vehicle to manage the battery's unique demands.
That line of argument, however, it sort of shifts the discussion away from maximizing motor performance, which directly impacts the user experience and the vehicle's capability. The trade-off you are defending involves accepting inferior motor temperatures for the sake of what you term segregation and system protection.
Well, let's talk about the cost of that thermal precision then. High-precision, actively pumped oil systems, such as the one used by Tesla, they come with tangible engineering costs, increased mechanical complexity in the pump apparatus, higher production costs, and a real compromise on energy efficiency due to the parasitic load. That system, as noted, demands additional electrical power to run the oil pump, slightly compromising the motor's inherent efficiency advantages. For a mass-market vehicle, reliability often correlates with simplicity, and active oil pumping definitely complicates things.
That's a compelling argument against high-pressure active systems, I agree. But have you considered that oil cooling doesn't have to be high-tech or high-energy draw? General Motors, interestingly, employs a simpler, gravity-fed passive oil cooling system in some of their drive units.
Ah, yes, the passive system.
Exactly. This is an inherently simple, economical mechanical solution that consumes very little energy because it eliminates the active pumping mechanisms entirely. It shows that the complexity and energy costs associated with the pump are not inherent defects of oil cooling itself, but rather a choice in design, active versus passive.
That choice highlights the issue, though, doesn't it? GM prioritized simplicity and low energy draw. But that passive system is most effective at high speeds when the oil is naturally flung onto the rotor and windings. In low-speed traffic or slow driving conditions, that circulation is inconsistent, potentially compromising thermal management, just when component sensitivity might be highest in stop-and-go driving. This inconsistency is precisely what the robustness of a dedicated, pumped liquid loop seeks to avoid.
You're right that active systems offer consistent performance across the full speed range. But we also see middle ground solutions that try to bridge the gap. Renault, for example, utilizes a pragmatic, liquid-cooled pumped solution that cools the motor, battery, and principal components uniformly through a less aggressive liquid path. Now, while this doesn't achieve the highly targeted cooling of, say, oil jets, it does balance effectiveness, simplicity, and cost, which suggests that the indirect liquid path isn't strictly outdated, it's just perhaps a less performance-focused compromise compared to the direct oil approach.
I suppose I come at it from a different angle. If we look at the trajectory of design philosophy, the movement toward tightly integrated electric drive units, e-motors coupled directly with transmissions, that naturally favors oil cooling. Why? Because the single dielectric fluid can efficiently handle both the required gear lubrication and the extremely high thermal demands of the motor core simultaneously. This consolidation seems like a crucial future trend.
Exactly. This consolidation maximizes power density while simplifying the overall mechanical structure, making the whole drive unit smaller and lighter. It seems almost inevitable for performance vehicles, doesn't it?
But complexity is often necessary, not a defect, when guaranteeing thermal protection across highly sensitive, expensive non-motor electronics, like that single power inverter module or the DC-DC converter. A less targeted liquid system, even a sophisticated pumped one like Renault's, arguably carries a slightly higher risk in intense or extreme use cases compared to the ultra-precise actively pumped systems like Tesla's, or indeed the inherent robustness of GM's dedicated, segregated architecture for those specific electrical components. When components fail due to thermal runaway, the costs are substantial, often requiring full drive unit replacement. Segregation is fundamentally a design safeguard against cascading thermal failures.
But the oil cooling methodology, particularly the precise targeted approach, is arguably a superior safeguard for the motor itself, which is where the bulk of the power loss and intense heat actually resides. By tackling the motor's heat aggressively, removing that potential 40 degrees Celsius excess, you drastically reduce the thermal burden on the rest of the system. This allows the heat exchangers that handle the general electronics to operate much more easily under less stress.
But you still must maintain a separate, highly efficient system to manage the battery during DC fast charging, which is perhaps the most aggressive thermal event the vehicle regularly experiences. We are still left with two separate thermal control objectives: high-precision motor cooling versus application-specific battery thermal regulation. The multi-loop segregated system, even if maybe less efficient for the motor in isolation, ensures that both objectives are met without compromising the other component's unique needs.
The massive thermal performance gains are absolutely justified, especially when considering the engineering push toward future power density. The energy spent running high-pressure pumps, or the engineering effort required to manage inconsistent passive flows is, I believe, outweighed by the ability to achieve smaller, more powerful e-motors that fundamentally change the vehicle's performance envelope.
And I maintain that the inherent complexity of specialized thermal needs, specifically the requirements for battery heating, sustained fast charging, and the precise temperature limits of passive electronics, necessitates dedicated, separate loops to guarantee stability and prevent cascading failures across the vehicle's entire operational range. The trade-off in motor efficiency is, I think, acceptable when weighed against overall system robustness.
It is fascinating, though, to see these two distinct engineering philosophies, one focused on protection and segregation, the other focused on thermal performance and integration, really defining the technology of thermal management today.
Absolutely. So, to summarize my position, for comprehensive reliability and managing those diverse operational demands, separate and specialized liquid coolant loops provide the necessary layer of robust, application-specific thermal safety. The complexity is, in effect, the cost of achieving absolute certainty across all vehicle functions, from charging to high-speed driving.
Conversely, the quantitative thermal advantages of direct oil cooling, lower component temperatures, protection for critical permanent magnets, and enabling significantly higher power density signal that this integrated architecture is the definitive solution for maximizing performance in future EV motors. It's pushing the industry away from reliance on indirect liquid jackets.
The difference between the pragmatic, multi-loop liquid systems of many current EVs and integrated, high-performance oil cooling systems potentially for tomorrow really highlights that this critical optimization pathway is still an open and evolving question for the industry.
Indeed, The focus remains firmly on how best to dissipate heat without sacrificing efficiency, longevity, or performance. It's a key battleground for EV development.
Thank you for joining us for this in-depth exchange on thermal management strategies. We hope this was clear and insightful. We encourage you to follow our channel so you don't miss our next discussions on the deepest technical issues facing electrification. Goodbye for now.